Hey everyone, welcome back to Chem Story. Today, we're going to talk about how electrons move during chemical reactions. Understanding how electrons shift around is super important. It helps us predict and explain how reactions actually happen. We'll take a closer look at electron movement in both polar and radical reactions, and we'll focus on how lone pairs, bonding pairs, and unpaired electrons shift during each type. Let's go step by step and break it all down. So let's start by looking at how electron pairs move in polar reactions and what kinds of steps are typically involved. Polar reactions involve the movement of electron pairs between atoms, usually because of differences in electronegativity. And we can break these reactions down into four main types: nucleophilic attack, loss of a leaving group, proton transfer, and rearrangements. Let's start with the first one: how lone pairs move during a nucleophilic attack. In many polar reactions, nucleophiles use their lone pairs to attack electrophiles. A nucleophilic attack happens when an electron-rich species donates a pair of electrons to an electron-deficient atom, like a handshake, where one side has extra electrons and the other is ready to accept them. For example, hydroxide can attack ethyl bromide, donating its lone pair to the carbon and kicking out the bromine to form ethanol. The same thing happens when ammonia attacks methyl bromide. A new bond forms there too. So how do the electrons actually move in these reactions? Let's break it down. The nucleophile donates its lone pair to the electrophilic carbon, and you'll see a curved arrow from the lone pair to the carbon. At the same time, another arrow shows the carbon-leaving group bond breaking, with electrons shifting onto the leaving group. Back to the hydroxide example. The lone pair on oxygen attacks the carbon, pushing the electrons in the CBr bond onto bromine. Bromine leaves as Br-, and ethanol is formed. Same thing with ammonia. Nitrogen's lone pair attacks the carbon, the CBr bond breaks, and Br- is released. This whole sequence, the attack, bond formation, and departure, is what drives nucleophilic substitution reactions. But nucleophiles don't just attack alkyl halides, they can also go after carbonyl carbons using their lone pairs to kick off the reaction. For example, when hydroxide attacks the carbonyl carbon of a ketone, it forms a tetrahedral intermediate. That happens because the carbonyl carbon is electrophilic. It's electron deficient, so it makes a perfect target for nucleophiles. But this kind of reaction has something a little different going on. The carbonyl group has a pi bond between carbon and oxygen. So when the nucleophile attacks, that pi bond breaks. And those electrons don't just vanish, they shift up onto the oxygen, forming a negatively charged oxygen anion. This shift in electron density helps stabilize the intermediate and allows the reaction to move forward. In some cases, like in intramolecular reactions, that oxygen anion can actually swing around and attack its own carbonyl carbon. That leads to ring formation. And this is a really important mechanism in both biological and synthetic chemistry, where nucleophiles drive ring-closing reactions by attacking electrophilic carbonyl carbons. Next, let's talk about how leaving groups leave. When a leaving group breaks away, it takes a pair of electrons with it. And what happens after that depends on whether the starting molecule was negatively charged or neutral. First, if the substrate starts off with a negative charge, losing the leaving group actually neutralizes it. The leaving group walks away with the electrons and with the negative charge. A good example is when a tetrahedral intermediate, formed by nucleophilic attack on an acid chloride, collapses back into a carbonyl. In that case, the lone pair on oxygen reforms the double bond and kicks out the leaving group, usually chloride, Cl-. Now, what if the substrate is neutral? Then, when the leaving group takes the bonding electrons, it leaves behind a positively charged molecule, a cation, and becomes a negatively charged anion itself. You can see this clearly in SN1 and E1 reactions. Take tert-butyl chloride, for example. When it ionizes, the chloride ion takes the electrons and leaves, forming a tert-butyl carbocation and a free chloride ion. In some cases, the leaving group needs a little push before it can leave, and that's where protonation comes in. By adding a proton, the leaving group turns into a neutral molecule, which makes it way easier to break off. Meanwhile, the rest of the molecule ends up carrying a positive charge. A great example of this is when tert-butanol reacts with hydrobromic acid. In this reaction, HBr donates a proton to the hydroxyl group, turning it into water, which is a much better leaving group. Once it's protonated, H2O breaks away, and that leaves behind a highly stable tert-butyl carbocation ion. And depending on the conditions, that carbocation ion can go on to react through either substitution or elimination. Alright, now that we've covered how leaving groups leave, let's move on to another key process in reaction mechanisms: proton transfer, a fundamental step in acid-base chemistry. One example of proton transfer is when an amide anion acts as a base and pulls off the terminal hydrogen from an alkyne. That gives you an acetylide ion, which is a really strong nucleophile and can go on to react in other steps like alkylation. You'll see something similar with a hydride. It can also act as a base and remove a proton from an alcohol. That forms an alkoxide ion, and compared to the neutral alcohol, it's a much stronger nucleophile. This kind of transformation shows up all the time in organic chemistry, like in the Williamson ether synthesis, where an alkoxide reacts with an alcohol halide to form an ether. Now, let's look at a case where the substrate itself donates an electron pair and acts as a base. Under acidic conditions, the oxygen atom in a carbonyl group can donate one of its lone pairs to a proton, and that leads to protonation. Once that happens, the carbonyl carbon becomes a lot more electrophilic, which makes it more reactive toward nucleophiles. You'll often see this kind of activation when carbonyl compounds react under acidic conditions. It's a key step in transformations like acetal formation and esterification. Now let's shift over to electron movement in shared electron pairs. This kind of movement shows up in reactions involving pi bonds and sigma bonds. A great example is the addition of HBr to an alkene. The hydrogen from HBr bonds to one of the carbons in the double bond, and then the Br- ion attaches to the more stable carbocation ion that forms. The same idea applies to alkyne additions too, though the reaction conditions and the final products can be a bit different. Benzene goes through electrophilic aromatic substitution, where bromine, activated by FeBr3, reacts with the ring. But the movement of electron pairs isn't just something you see in substitution reactions. It shows up in all kinds of mechanisms. Another important example of shared electron pair movement is reduction. A classic case is how sodium borohydride reduces carbonyl compounds. Here's what's going on. NaBH4 donates a hydride ion, and that hydride carries a pair of electrons that attacks the carbonyl carbon. When that happens, the carbonyl pi bond breaks, and the result is an alcohol. Now, that electron pair actually comes from the sigma bond between hydrogen and boron in NaBH4. When that bond breaks, the hydride takes the electrons and delivers them to the carbonyl carbon. At the same time, the pi bond in the carbonyl shifts its electrons up to the oxygen, and that helps stabilize the intermediate. That's why NaBH4 works so well as a reducing agent. It delivers a nucleophilic hydride straight to the electrophilic carbonyl carbon, and the product is a stable alcohol. Another type of electron pair movement happens during alkyl shifts. In this case, an alkyl group actually moves to a new position, and it takes its bonding electrons with it. These shifts help stabilize carbocations by redistributing charge. What's happening is that one sigma bond breaks, and a new sigma bond forms somewhere else, letting the molecule adopt a more stable structure. Finally, let's talk about how electrons move in radical reactions. Radicals are species with unpaired electrons, and they behave very differently from what we see in polar reactions. It all starts with homolytic cleavage. That's when a bond splits evenly, and each atom takes one electron from the bond. This kind of bond breaking is usually triggered by heat or light. Now, if you flip that around, you get radical coupling, where two radicals come together and form a new bond by sharing their unpaired electrons. Radicals can also react with CH bonds in a process called hydrogen abstraction. That's where a hydrogen atom, along with its bonding electron, gets pulled off by the radical. A similar thing happens with CX bonds in what's called halogen abstraction. Here, a halogen atom is transferred in the same way. The radical takes the atom and its bonding electron in one step. For example, a halogen radical can attack methane, pulling off a hydrogen atom and leaving behind a methyl radical. That methyl radical can then react with a halogen molecule to form a new bond. So how do the electrons move in this process? The halogen radical has an unpaired electron, which makes it super reactive. It collides with methane and pulls off a hydrogen atom. The CH bond breaks evenly. One electron stays on the carbon, and the other pairs up with the halogen radical to form HX. Now you've got a methyl radical left behind, and it's ready for the next step. That methyl radical then reacts with a halogen molecule. It donates its unpaired electron to one of the halogen atoms, forming a new CX bond. At the same time, the XX bond breaks homolytically, and another halogen radical is released, ready to keep the chain going. This cycle repeats over and over, driving the reaction forward, until eventually, two radicals find each other and combine, shutting the reaction down. Radicals can also interact with pi bonds in alkenes, and that leads to radical addition reactions. The reverse of that is radical elimination. In this case, a radical species kicks out a halide, and that results in the formation of a new pi bond, basically forming a double bond in the process. These types of reactions are super important in polymerization, where radicals help link together monomers into long chains. You'll also see them in lots of other organic transformations that involve building or modifying carbon frameworks. In some cases, a radical can react with a pi bond within the same molecule, and that leads to intramolecular bond formation. For example, in certain cyclization reactions, a radical formed on one part of the molecule can swing around and attack a nearby alkene. That forms a new sigma bond and creates a ring structure. Alright, that wraps up our discussion on how electrons move in chemical reactions. Today, we looked at how electrons shift in all kinds of reactions, from nucleophilic attack and proton transfer to rearrangements and radical mechanisms. Once you get the hang of these patterns, it becomes so much easier to understand and predict how organic reactions work. By mastering these fundamental ideas, you'll be able to break down mechanisms with confidence. Thanks for watching, and I'll see you in the next lesson.